our main, and this reemergence has been our main topic. And of course, Amsterdam is still in the Netherlands, so I thought, let's do it. I still have a few PhD students, obviously. Is it okay? Gaat het goed zo? Okay, yeah. So this is about our work on collective motion in bird flocks and fish schools. And here you see an example of the dancing of starlings above a sleeping site. And you see how the flock changes its shape and how it changes density, it seems. And here you see a peregrine falcon at the top left attacking the flock, and you see the dark bands move downwards. And this is what we call an agitation wave. The reaction of the flock is called an agitation wave. So you see here the peregrine falcon attacking. And we have used models of self-organization in which we represent individuals in three-dimensional space with cognitively simple behavioral rules. And then we have studied how their interactions lead to emergent patterns by self-organization, complex patterns at a group level. And if they resemble empirical data, then we have gained some understanding by building the system, and we can derive hypotheses for empirical data. And this talk, I will give examples of patterns emerging without a predator, and then we concern the shapes of flocks and the internal structure, and when under attack of a predator, and then we look at traits of a flock that confuse the predator, patterns of collective escape like the agitation wave, and different patterns of collective escape in different species of bird when attacked by a robotic falcon that we developed. And fish schools are having an oblong shape, so that is longer than wide. And this is remarkably different from what we see in flocks of birds, because bird flocks have all kinds of shapes, like you see here. And in the 1930s, it was argued that the flocks of birds are happening by telepathy. And but we are now studying, of course, this is not true, and we are now studying what causes this difference in the rather static shape of the school of fish and variable shape of flocks of birds. And it has been argued that the variable shape, that the oblong shape is adaptive of fish schools because the predator comes from the front and then it's difficult to detect. But of course, the predator can come from all sides. It's not a good argument. If it comes from the side, it sees a very big shape. So we rather ask, how is it organized? By cognition or by self-organization? How do they make this shape oblong? And this we study by building a computational model. Like you see here, we have individuals in a three-dimensional space, and they interact with their local neighbors, and they are attracted by those that are close by. They align their heading with those at intermediate distance, and they avoid collisions with others that are further away. And in this model, they do this by slowing down. And what we see is that automatically the shape of these schools is oblong, longer than wide. So we measure the shape like this. We put, here's the school colored in colors, and we put a line for the longest length and a rectangular around it. And we measure the width like this, the broadest width. And if we divide length divided by width and it's above 1, obviously the school is oblong, longer than wide. And what we see is that for all school sizes, like you see here, till 500, it's always oblong. And this happens in models that are developed in 2 dimensions, models that are developed in 3 dimensions, models that we developed of all kinds of group sizes up till 5,000, for different cruise speeds, for different body sizes of the fish, also mixed groups with mixed body sizes. Always the school shape is oblong. Now the question is why or how? And for this we studied in the model We started in the model the school in the form of a bowl shape, like you see here. You have 600 fish, and they are in a shape of a bowl, and then we let it go. And what we see is that over time on the x-axis, the length increases and the width decreases. So it becomes more and more oblong, narrower and longer. And we think that happens as follows. Here you see 4 fish as a caricature, and you see that the black fish is a bit close to the frontal fish, and as mentioned, if they want to avoid collisions, they slow down. So what we see here is that the black fish slows down at the next time step, which leaves a gap here in the middle, and we see that the fish at the side, they move inward, and therefore the school has become oblong. So we think this model shows that the school becomes oblong because individuals avoid collisions. And this is a testable hypothesis. What we saw in the computational model is that with larger school size on the x-axis, you see that the length divided by width increases, the school becomes more oblong. And with larger school size, you see that the average distance to the nearest neighbor decreases. So the school becomes denser. And then obviously you can imagine that if the school becomes denser, they need to avoid neighbors more often. If they need to avoid neighbors more often, they slow down and the school becomes more oblong. So this is an empirical, this you can test empirically.
Charlotte, do you mind questions in between, or do you want to add here?
I have cut the whole talk in 4 sections. Okay. So after this about the fish school, there's a moment for questions. Is that okay for you, or is there something unclear at the moment? No. Okay. Then I think it's good. I've cut it with 3 times for questions, and at the end, so 4 times for questions. Good. So what we did is we studied with IJzer Stamhuis at the University of Groningen fish in the tank, and this tank, as you see, is of octagonal shape, and in one part of the tank, this part of the tank, we put a wall, and on this wall we hang a mirror under 45 degrees, which means that, like you see here, we can see the same fish. This is the same fish, both from the side and from above, so under 2 angles. And so this means we can derive the 3-dimensional positions of the fish. And this we did for schools of 10 to 60 individuals. And at that time, that was the largest number of individuals who tracked 3-dimensional position of individuals tracked for schools of fish. And what we see in this case is that the length divided by width is always larger than 1, but also it increases. It becomes more oblong if the school is larger. And also we see that in these fish, the school becomes denser, the nearest neighbor distance is shorter, the larger the school size. And here we have then a difference between the empirical study and the modeling, because in the modeling they are swimming freely, but in the empirical study they are swimming in a tank. So what happens now if we put the fish in the model in a tank? And that's what we did. So we added to the model this tank-like structure. Here you see it. The tank. Oh, do you see my cursor? No. We add this tank-like. Wait a minute, I have something weird here. Okay, so this tank-like structure, where you have, because of the mirror, a narrow part here, and then you have a wide part here. And so we look what happens. And first we confirm that if we have this tank-like structure and the wide and the narrow passage, that if the school size increases, for larger school sizes, the schools are more oblong. So that's like before. But now we want also to know what is the effect of the avoidance of the wall, because we added avoidance of the wall in the model. And what we see is that the school is most oblong in a narrow passage where they will have to avoid the wall most often. Intermediate in wide passage, and in the free study, it's least oblong. So more avoidance of the wall means more oblong. And the nearest neighbor distance, you see also that in the narrow passage, the nearest neighbor distance is shorter, so they need to avoid also other individuals more often, not only the walls, than in the wide passage and then in the free case. And then we looked at the local polarization, that is the alignment of the heading of the individuals. And you see that in the narrow passage, the alignment is the lowest, which means they are needing to avoid each other most often. And in the wide passage, it's more, and the alignment is strongest if they are free. So the avoidance of the walls in the model causes extra that the school shape becomes oblong, the nearest neighbor distance shorter, and the polarization weaker. Next slide. Oh, yeah. So the oblong shape of fish schools emerges from collision avoidance and in a tank from the avoidance of individuals with the wall. And what we see is another emergent pattern, and that's what you see here. So this tank has an octagonal shape, and what we see is that in this tank, the blue lines, if there's a single fish, it moves like this red line. But if there's a group of fish, they take a shortcut. And this is in the model, and this is also in empirical data. In empirical data, you see that the distance to the inner wall is shorter in small schools, and larger in small schools and shorter in large schools. And how does this come about? That you can see here. Here we have a school of fish in the model, and we take out fish, and you see that it goes more and more away from the inner wall, and when they are in a group, they are closer to the inner wall because maybe you see it already. The frontal individuals are turning, and the individuals at the back are then earlier turning because the frontal individuals are turning. So the information is transferred. So individuals at the back of the school start turning sooner because the frontal individuals are already turning when they are in a school than when they are alone. So questions, yeah. So this is, yeah, zeg maar, yeah.
Two questions.
Yes.
First of all, is the oblong shape, does it depend actually on the strength of the avoidance and the attraction?
So does the oblong shape depend on the strength of the avoidance?
Yeah, you have to.
And the attraction? Yes, it does, because if you have a lot of attraction, then you would have that the school is rather dense. And if the school is rather dense, this means that you need to avoid each other more often. Yeah, so it does depend on these things.
But it is in all conditions, in all situations, you have actually an oblong shape, independent of. I mean, it may be a different form of oblong shape, but
yeah,
it's always oblong.
It's always oblong. So it's always oblong. And the remarkable thing is not only oblong if you make collision. You can do collision avoidance in several ways. One way is make the individuals that are too close to others slow down. That's what's in this model. But in our former models, we had individuals that are too close to others turn away. And also then you get the same oblong shape, because if they turn away, then the rest is still moving forward and they are falling back. Yeah.
And my second question is about these dots that in the free individuals, which you had in the inner, this octagonal shape. One of the previous slides was. So this one.
This one?
Yeah.
Yeah.
So here the free individuals, as I understand it, is they are in an octagonal shape.
No, the free individuals are in the former model. So the model where there is no tank.
Okay, why
Sorry.
don't I see any decrease in the mean nearest neighbor distance in the free individuals here?
There is a decrease in the mean nearest neighbor distance in the free individuals. Yeah,
Because
it's like you don't see it there because it's this one. This is the free individuals. So the larger schools, yeah. So it is there, but you don't see it because of the scale is very different between the different passages.
Okay.
Yeah.
I have a question.
Yeah.
Could you put back to the slide where you have the trajectories like a plot of the octagons?
Yeah, you mean the circling?
Yeah, this one.
Yeah.
Okay, maybe it's just illustrative, but I understand your argument. But from the picture, I only see that's closer to the corner in the left bottom corner. But your argument would work for every corner. So is it just an illustration, or every corner the more later one they are closer to the turn to the octagon?
I don't really get your argument. What I say is that in the whole octagonal tank, it's not just a corner. I don't get your argument. You see that in a group, they're closer to the inner circle.
Yeah.
They're closer to the inner circle, the whole group, in green, always, than if it's a single individual.
Ah, I think, sorry.
That was the argument. Yeah, okay, good. Thanks. You asked. Huh?
Yeah, I think he was asking why the circle is not symmetrical.
Yeah,
It's the other way.
Yeah.
Why is it closer to certain parts?
That is because the octagonal thing is not symmetric. Because you see, this is the narrow passage and this is the wide passage, and that is because we have this. We have this mirror hanging here, and that means that this passage is smaller because there's an extra wall, and this here. So this is an octagonal tank, but the mirror is here hanging on an extra wall. So this is a small passage, and this is a wide passage. I did write it here. Here you see the wide passage, small passage. Yeah.
Can I ask something?
Yes.
So normally in physics, we think that we can model these things using the V-check model.
Yeah.
Which is, it's a model of alignment.
Yeah.
You have, and it's typically just near neighbor interactions. So you have some alignments at each point in some position, and then they see how many individuals are aligned in a certain direction, and they take an average and they update that their alignment in the next step. And normally people say this is okay for describing flocking and this kind of stuff, but it doesn't have these other factors that you put in, like you're having more than just near neighbor interactions, because you're looking at avoidance or alignment, I don't know, with individuals which are further away than the nearest neighbors. I was just wondering, does that model fall short on something, the V-check model?
The V-check model does fall short, absolutely, because the V-check model has no attraction indication. The way you describe it, it has only alignments.
Yeah.
So there will not be groups.
There will not be groups?
There will not be groups. The groups are only there because in the V-check model, he starts them close together, the individuals or the particles, whatever you call it. Mm-hmm. So in animals, if you think about animals or real self-propelled individuals, now we would say autonomous agents.
Yeah.
If you think about autonomous agents, to get groups, you have to be attracted to each other, which is not in the case you tell the V-check model. It falls short there, yeah. It falls short. It falls also.
It's assumed that they're attracted because they're always, they're in some positions, right? And they're not wandering off. They have a velocity.
But that's only because they have probably the same velocity and they start close to each other.
That's true,
Which is definitely unrealistic for reality. In reality, individuals have to be attracted to each other, and they and by aligning, and in the V-check model they may overlap if they would have different velocities. If the individuals would have different velocities.
Yeah.
But in a model like this, if the individuals have different velocities, they will slow down and speed up in this model, like the real animals. Yeah, so it falls short on that, yes. Okay, wacht even. Oh, wacht even. Ja, ik weet niet wie is.
Well, I was wondering
Say again.
about this question also about the interaction and on length scales this happens. So you have these three effects. You have this attraction, repulsion, and alignment. So all these three effects have their own length scale, or not? In the sense that
In this case, yeah.
So how do you decide these length scales?
Yeah, but
What's
we.
the interplay between if you change the.
You are totally right. So you decide these length scales in general by the general argument avoidance is close by, where you. Okay, you have these three behaviors: attraction, alignment, and avoidance. And the strongest avoidance is close by. Alignment is intermediate, and you're attracted over a certain distance. That's largest. Yeah. So that's the rough scale, and the precise scale you determine per model with all the differences of small differences of the different models, so that you get a school that stays together.
So you calibrate so that it's together.
You calibrate, yeah.
You don't have explicit. Actually, my question was more around this question. You don't have an explicit formula for the interaction. Like I'm coming from physics, we typically.
Yeah, we have formulas for the interactions. Yes. Yes, I didn't show them. Yeah.
And just following up on this question, like, is this space of parameters of this calibration is a stable, is a large space that keeps these blocks?
Yeah. Yeah. So you have basically in this you can do it in many ways. In this case, we have three forces: attraction, alignment, and avoidance, and they have a parameter in front of it. And these parameters you tune, and they are fixed for the whole model.
What's the form of attraction? Is it power law? Like how does it look? Like do you have?
Yeah, it is like this one. Like this one. So this is slowing down to avoid collision. I can show you afterwards. Is that an idea, or should I show it now? Because I have it in the different PowerPoints.
Yeah, thanks.
Okay, shall I then continue? And so we were starting with the question: why is there this big difference between flocks of birds and schools of fish? Flocks of birds have a great variation in their shape, and schools of fish don't. So why is that? And so we took the same model, in the sense we took this core of the same model, the coordination and emotion that they move and that they're locally coordinating is like in the fish school, in the sense that we have attraction, alignment, and avoidance. But the difference is that these attraction, alignment, avoidance is not over different length scales in this case, but it is always with 6 to 7 neighbors. And that is because the physicist in Rome studied the three-dimensional positions of starlings in flocks and discovered that they tune their behavior to their 6 to 7 neighbors, and it's more or less random. And the other individuals are more or less random relative to the ego you look at, the individual you look at. So we make them interact with 6 to 7 neighbors, and they are attracted, aligning, and avoiding these 6 to 7 neighbors. And in addition, they are, in Rome, they are circling above a sleeping site, and in other locations also. So we represent the sleeping site by a circular area, and when they're outside, they come back to it. And then we wanted to represent in a very coarse way the aerodynamics, in the sense that they roll over their shoulder when they have to turn, and they are feeling gravity, lift, thrust, and drag. And we tuned the model with what we knew from empirical studies, like the reaction time is about 60 milliseconds, the cruise speed of starlings usually 36 km/h, the mass of most starlings 80 grams, etc. And then you have the radius of separation, so where they do not get any other bird closer to them, and that is their wingspan. So the wingspan to one side is 20, of one wing is 1/2 is 20 centimeter. And the whole wingspan is 40 centimeter, and this is so-called the hardcore, where others aren't allowed in. And the size of the area above they were circling, the roosting area has a diameter of 150 meters. And what we get is a flock like this flock. This is a flock of 5,000 birds. These models are made by Charlotte Hemelrijk. So this is a flock of 5,000 birds. And you see, and we measured lots of things in it. We measured the shape of the flock, the orientation of the flock relative to the floor, the internal structure of the flock, and it was all statistically similar to the measures for the same flock sizes measured in Rome. But what we saw is that the volume of the flock for the same number of individuals was too small. And now we come back to the question, why is this so variable, this shape of the flock? And I give now a number of arguments what makes the shape of the flock variable. And one of the reasons is that the birds fly, let's say, at almost fixed speed. They don't speed up and slow down. They fly at fixed speed, and all of the individuals fly at the same speed. And this means that if the flock flies in the shape of a wide shape, like you see here, this is the direction of motion, that if individuals at the left side before the turn, that after a turn of 90 degrees, like you see here, this is approximately a turn of 90 degrees, the individual that was initially at the left side at the end will be at the back of the flock. Is it clear? And the individual at the right side will be at the front of the flock. And the shape of the flock here relative to the motion, and you always talk about shape of a flock relative to the motion. The shape of the flock here is wide, and the shape of the flock here is oblong. And this means that with every turn of a flock of starlings, the shape changes, because the speed is fixed, all individuals have the same speed. And what we see is that indeed this is shown in starlings afterwards. And this had already before been shown for rock doves, that the shape of the flock before the turn is wide and after the turn is oblong. Another reason, and this is very different from what I just mentioned with what we think about fish schools, because we think that in a fish school, if it turns to the right, like you see here, then the individuals in the inner corner, like you see here, will have to slow down because they come too close to their neighbors, which is indicated in blue as an emergent property. And the individuals as an emergent property at the outside will have to speed up, which is what you see. And here you see snapshots, or let's say photographs of the school over, let's say, 14 time units, and you see that the shape of the school remains, despite that we see oblong, despite that we see that it turns in the fish school. And we see also that in this case, the position of the individuals remains the same within the school, because here we colored the individuals green at the left front, red at the right front, and you see that at T is 1, this is the case, and at T is 10, this is still the case. The same individuals are in the same location. And that is because they're slowing down and speeding up. And so they stay at the same location, which is very different from what we see here. Here, the individuals at the left side are later on at the back, because the individuals move as fixed speeds. This is a prediction, obviously, for empirical data. Now there's another cause for the variability of shape, and this is the flying behavior. And so remember, if you're cycling and you're cycling really fast and you go to the left under a sharp corner turn, you of course have to bang over your left shoulder. If you don't bang over your left shoulder, you will make a much weaker turn. This is what the birds do also. If they turn, they roll over the shoulder. But of course, if birds are flying like this, then they lose lift if they're flying like this suddenly, like you see them do here when they turn, they lose obviously lift. That's clear. Their wings are vertical. And that means that they move downwards a little bit. So during a turn, the flock moves downward a little bit, which causes the shape of the flock to lengthen vertically during turning. And that is what we show here. What you see here is that this is the shape of the sleeping side, and this is the center of gravity of the flock and the trajectory of it. And let's say at 30 seconds, you see that the flock makes a sharp turn, yeah? And here at 30 seconds, so this is the time on the x-hat, you see that the altitude goes downwards, lowers at 30 seconds. So indeed, the flock lengthens at the moment that they make a turn. It moves downwards. So what we did in the model is we took out this rolling behavior, because in the model, we make the birds roll when turning, so the lift changes. If you take this out, then what you get is what you see here. The flock stays in a banana-like shape and moves along this circular boundary, and you don't get the very wild shape you have otherwise. So this is another reason for the variability in flock shape.
Do you have a movie with rolling?
Yeah, there you have a movie with rolling. This is a movie with rolling, and also this is one of the movies with rolling, and these are also 20,000 individuals. And what you see here is something extra, and that is that the shape is not simple anymore. It has become a complex shape, because what you see is there are pseudopodia. And you can imagine that this darkness is perhaps because some of the pseudopodia go in front, and so we see more individuals behind each other. Anyhow, these pseudopodia are a consequence of, let's say, the individuals coordinate with each other. But if the flock gets very, very large, then you have, let's say, subflocks coordinating. And that is what you can see here, and also measured in the empirical data. So in the empirical data, what they measured is different flock shapes. And here you have the flock size measured by the length on the x-axis of the empirical data. And what they see is that the correlation lengths of the heading or of the deviation, both of velocity, deviation of the average velocity of the swarm, of the flock, is increasing. So if you have a larger flock, you have a larger deviation of this velocity. And you can see that here too. This is for the model. We find the same in the model. If you have a larger flock, you have a larger deviation of velocity. And this deviation of the average velocity we color. So here you see the flock in the model, and you see the average velocity is blue, and you see that particularly when it turns, there's a lot of deviation of this velocity. And let's say the subflocks with the same correlation, has the same heading, are colored in the same way. You see the subflocks are small, obviously, because it's a small flock, and the subflocks are longer, obviously, because it's a longer flock. Otherwise, it wouldn't be possible, obviously. And this correlation length, how the length over which they are having a correlated heading, a correlated deviation of velocity, is a bit steeper increasing with the flock size in case of the model. And in the model, that's steeper because in the model, we have no disturbance. We have no disturbance by wind. We have no disturbance by another gull flying by, or by a predator, or obstacles. And so this is steeper. And then here is a short summary of this part. So the variation of shapes of bird flocks, and we look at starlings, arises from, when they're not attacked, arises from the physical constraints of flying behavior, which are that the birds are banking when they are turning, and that means they lose lift and therefore altitude. The variation in the speed among the individuals, and anyhow, is very small, and that means that the shape, or is absent, let's say absent, that means that the shape of the flock changes when turning for each turn. In the flock, the birds are asynchronously coordinating. They coordinate only with a few neighbors, which means particularly that for large flocks, there will be areas where some individuals already turn to the right and then others turn to the right, and so you get a kind of subflocks. And so with a very large flock, you can get pseudopodia, and so you can get also separate subflocks. So, and then if we look at the internal structure, what happens to this internal structure? People have argued, do they fly near their mother, these individuals? Well, they don't, because here we look at the stability after 3 seconds, so at the stability of neighbors. And what we look at is, in empirical data, at the percentage of neighbors after 3 seconds that remain. So at the beginning you have 4 neighbors, and at the end, after 3 seconds, on average, you have 40% of your neighbors left. And when we look in the computational model, this is rather incorrect, because we see that in the computational model, after 3 seconds, the internal structure is such that 60% of the neighbors is left. So we thought something is not good in the model. Let's look what happens if we make them avoid their neighbors differently, in the sense that they do not avoid the same number of neighbors they also are attracted to and they align with, but they prioritize to avoid their nearest neighbors, because that's the most dangerous. And the consequence of this, and here I show it in a caricature, is suppose you want to avoid only your nearest neighbors and you mind only 4 neighbors. Then this individual wants to avoid this individual, so it moves in this direction with this, over this length.
That means flying backwards.
Or decreasing speed.
It doesn't matter. It's a caricature. And here you see it avoids, in this case you see it wants to avoid, like we always had and all the models have, all the 4 neighbors. That would mean that theoretically it would avoid individual 1 like this, individual 2 like this, individual 3 like this, and individual 4 like this, which would be averaged to a compromised behavior. A compromised behavior whereby it moves not only in a different direction, but also less far. It makes less extreme movements. So if we do this in the model, if we compare this in the model, so that they avoid 6 or 7 neighbors, like we always did, or that they avoid 1 neighbor, then you see that after 3 seconds, if they avoid only the closest neighbor, the results are more similar to the empirical data. And this means that is it clear? So this means also that the volume of the flocks decreased, because if they have avoided, if they have reshuffled more, then of course they have a larger volume also.
Why is it not going even further down? Why is it 47, not 40?
Yeah, I don't know. That's a question of parameterizing, I think. So the stability of neighbors in the flock, the individuals avoid collision. If they avoid collision with fewer neighbors than the number of neighbors they are attracted or aligned with, that is what we think that really happens. So this is what would be an improvement of the model. So questions about this part, because then we go to predators.
If we were trying to avoid all the nearest neighbors, including the one behind them, it means they could somehow sense what's behind them, right? Or they're not looking.
Yeah, so they never, in the models, they never avoid those behind them. In the sense that
it was your figure, right? You had the 4 neighbors somewhere.
Yeah, in this figure. This is a caricature to show what the effect is of avoidance of more individuals,
Okay.
fewer individuals. But basically, they have so say this is the body of the individual. They have a sensory region like this for avoidance. So they avoid much more everybody around them, apart from a 90-degree angle at the back.
Okay.
Yeah, and you can do that different for alignment and for alignment and the other attraction. Yeah.
Yeah, there's.
Go ahead.
Well, the first part of the question is answered now, because it was also about the observability in the back. But if you compare this with fish, I mean, fish, you have these magnetic or electrical sensors at the side. I think
Yeah.
fish have these kind of things, and birds don't have this. So does this some sort of matter in the modeling that for fish they have more awareness of what happens on the side than a bird does, because a bird can only see and not sense anything on the side.
Yeah, that is not true, of course, because of course birds do sense something at the side. They feel the wind in their wings, and they feel. So the birds have their eyes at the side, and the birds are represented here as perceiving in a circle around them, so to speak, with a dead space behind them. But you can, for fish, make models where you represent, because fish are often represented as a dot, and then the sensory regions around it. But you can, of course, represent fish also more as a stick or as an oblong shape, and then you can also represent in their sensory regions more oblong. Yeah, and that has certain consequences indeed, but not very big. Yeah.
There's a question on the chat also, which is about the drafting of birds behind another. For instance, the models incorporate drafting of birds behind another. Why do duck and geese form these V shapes when they fly?
Yeah, so duck and geese, so in duck and geese, or rather geese, and so birds with long wings, you can imagine they benefit a lot from the air, from the airflow below them. Now, if a bird has long wings, then if it flaps these very long wings, you can imagine that at the tip of the wing, the air is streaming upwards. Yeah, and that means that if the next bird flies behind it, such that it catches the air moving upwards from the bird under corner before her, then it benefits from the upward streaming of the air. How do you call it? Upstream of the air. Yeah. And that's why the birds that have long wings fly in V formations, because they benefit from this upstream of the air. And starlings don't.
So I was just wondering that in the slide where you compared with the empirical data, so what happens if I, like in the model simulation, what happens if I simulate for a longer time? Does the percentage of neighbors still go down and like everything changes, or like for
Yeah. The percentage of neighbors, we never did this, and the empirical scientists did not do it, but the percentage of neighbors that's the same, of course, that goes down. Because there's a kind of a diffusion, so to speak, or a reshuffling in a flock going on.
So for a longer time, nobody like.
Yeah, nobody will be the same. Absolutely. Unless you have a group of 4 individuals, then of course. Very small flocks.
And if this change the weighting of the neighbors, and it's like, or suppose I take 2 neighbors, the 2 nearest neighbors, are you going to end up somewhere in between 7 and 6? Or like
60 and 70%? What do you mean 7 and 6?
Are you going to end up in between? Because the 7 neighbors goes to 60%, and then 1 neighbor goes to 47 or something. But I can imagine other weightings of my neighbors. Like I don't have to take all neighbors into account equally. They go.
No, well, you have to, now there are several things. If you talk about avoidance, we thought you can easily think of avoiding the most close neighbor, because that's dangerous. But you can also then, your question may also relate to alignment and attraction, which is perhaps stronger to individuals front ahead of you and less to individuals side or something. Yeah, you can do all these kinds of things. Yeah.
Maybe related. Because I'm not expert in this, but the distribution of neighbors, let's say on the corners, on the boundaries of the flock, are kind of different. So would this interfere in your, like, the 7% could be hidden in such a viability?
Yeah, we have, the physicists in Rome have observed that the border of the flock is rather streamlined, a bit, yeah. And we have, you have to understand that that happens because at the border of the flock, they are attracted inwards. And of course, within the flock, they're attracted in all directions. But at the border of the flock, they're attracted inwards. So you get a kind of surface pressure. Does it relate a bit to your question?
Yes, and so, but whether that changed the, how you would check for neighbor stability in the border, so if you would. correct-
How do you would acoustically?
In your diagram, I
Yeah.
assume you may assume everything is homogeneous, but the border, as you just explained, is not the same as within the flock. So whether that, if you would correct for the border, you would have better accuracy in your neighbor stability.
Well, there are many ways in which you can get more neighbors. You get more similarity. You can increase similarity. That's what you ask? How can I increase the similarity with empirical data? There are many ways, but we want ways that are relevant. So that we didn't try it, but you can certainly increase that. But then you have to find a relevant way, yeah, to do that for animals.
Yeah, I think his question was, is the edge dynamics a relevant way of decreasing that?
Yeah, we don't know. That we could try, but we didn't try. Yeah, that's a good question. Yeah.
These pseudopodia, are they also observed in empirical cases?
Yeah.
Okay.
Shall I show later on in the talk? Yeah.
Interesting.
Yeah.
And,
Yeah. Also in fish schools, huh? Yeah. But I show for starting flocks, yeah.
So
Yeah.
can I go back just to this little detail? Because for the fish, you told us, or you told me at least, it was very important that they had different speeds. While now, here, it seems that the physicists in Rome have realized there's not so much difference between speeds in these flocks.
Yeah.
So yeah, but still,
Among the
you
individuals?
still see an oblate shape. So I wonder how important the difference is.
I don't get your question.
Why was it so important that in the fish schools there was a large variability between speeds of individuals, while in the flocks there is no variability?
Yeah. And that is important because if there is no you get this. So the birds, so after we have published it, there was a publication of the physicists in Rome that they are rather static in speed among the individuals and over time. So if you don't start flying and are attacked by a predator, and the similarity in speed among the individuals and the same speed going on means that the individuals are all the time following the same curvature when they are turning, and that's what they showed later on in also in starlings. And this means that you get this change in shape all the time.
And that's different than for the fish, is that what you're saying?
Yeah, I try to explain here.
Yeah, okay.
I try to explain here. If you have a computational model in which you make them slow down, then automatically the fish in this model in the inner corner meet their neighbors ahead of them more and slow down. So you get the blue color inside and you get as an emergent property the green color outside. And you get that the individuals stay more or less at the same location in the flock. That's what you see here. The shape stays the same. These are pictures of this model over time.
Yeah, got it.
Yeah, and just a clarification, you mean they have a sort of constant speed, but in absolute value, because it's changing direction all the time, it's also changing speed.
I can't understand what you say acoustically. Say it again. They have very little. Okay, I can show you. Maybe this. I understood what you said. This is the variability of fish speeds, and this is the variability of bird speeds.
Okay.
Yeah. So there's hardly any variability
Yeah, but I mean,
in speeds.
when you see the flock, this is the variability of the absolute value, or it's variability also in the direction, because
The alignment is a different story, right?
Yeah, this is not about the alignment. This is about the speed, the absolute speed. The absolute speed is, and you can imagine the absolute speed is rather fixed because, of course, if you slow down as a bird, you fall down out of the air. so to speak, exaggerate a bit.
But part of the story was also that if the flock gets larger, the variability in speed increases, the variance.
Do you think about this one?
Yeah.
So this is something different. No, this is something different. This is not about speed. This is about a deviation in velocity. So it's related to heading.
Heading as well.
Yeah.
So the speed stays the same, but the velocity changes.
Yeah, so in larger flocks, you have a larger correlation length of the heading, which is obvious, because you couldn't have a large correlation length if you're a very small flock. But you do not need to have a large correlation length if you have a large flock, but they do. And they do both in the model and empirical data.
Just continue to the same, but comparing to the fish, so could be some sort of conjugation, so the distribution slope for the speed of the fish is the opposite for the direction of the birds, and then the direction of the fish is really narrow.
I don't get what you're saying.
Like, because you see that there's a narrow distribution for the speed in the birds, and a large one for the fish. But when you see the alignment, there has high variability for the birds and narrow for the fish. You can have...
No, I wouldn't say that. So you think that the alignment could cancel the... I wouldn't say that. So I can't compare the degree of alignment in fish schools versus bird flocks. I can't, but I can say something what I think, and that's rather similar. I think it's even stronger. It's a bit stronger perhaps in fish. I don't know. Could be studied. I don't know. Yeah. Shall I continue?
Yeah, I think it's good to continue.
Waar zijn nog iets
We already
zeggen?
asked.
What?
Please continue.
So please continue. Yeah. Okay. So now we go to the predators. And why are they in a group? And then biologists will say they are in a group because this is very good to be protected against predation. And one of the ways in which individuals protect themselves against predation is by confusing the predator, in the sense that if there are many prey in a flock, it's very difficult for the predator to target a single individual continuously. Because if it targets a single individual, others will move in between and it gets lost, it gets confused and starts to target a new individual. And so it takes time, and so this helps the prey. And this has been shown, this so-called confusion effect, in mammals, also in humans, if you want to pinpoint somebody in a crowd, but also in birds, in fish, and amphibia, insects, crustacea, mollusks. And in general, it is, of course, very difficult to study this in flocks of birds, particularly because you hardly ever see a predator attacking a flock of birds. So we study it now in the computational model. We study confusion of the predator, and the predator is the human. So we have a, how do you call it again?
Joystick.
Joystick sense. We have a joystick and the human in front of the computer. These were students. And it is a game. They steer the predator to attack they are very well. I couldn't do it very well. They steer the predator, they do so many games, to attack a pre-designed target. And the birds in the flock in the model, we use this computational model, do not react to the predator. And then we measure the distance, the fault they make, the error they make. How far did they click from the real targets? So what is the error? And then we want to know, so the inaccuracy, we measure the hitting error, the distance to the bird. And then we measure how it's affected by flock size and density. And so here you see the pre-designed targets, and the student is busy, it follows this, and then it hits, like you see here, and it was very well done, it was only 40 centimeters wrong. And then another student hits 0.4, so much worse. Another student hits 1.7 meter aside from where it should be. So we had a large sample of the students. It was a cooperation with people in Bristol. And you see that for the flock size, if the flock size gets larger, that the error of targeting by the students also gets larger. And that the largest error is in the dense flock, larger than in the looser flock. So density confuses and group size confuses. And this may also have an influence on evolution. Evolution may steer the individuals to make larger and denser flocks to be better protected.
Were these targets, preassigned targets, randomly in the flock or only on the outside? Because
Randomly in the flock.
predators would only select an outside individual.
Yeah, that's not true.
No?
No. No, it could be studied. It would be something that should be studied. Yeah. Like I show here, for instance, you see here that the predator is in, this is flocks of starlings, but I get your point entirely. This is flocks of starlings, and here in this vacuole is the predator, the peregrine falcon. So it's not the case, and sometimes you see even a peregrine falcon going all through the flock. Yeah. But I do agree that the impression is very much that they attack from the outside. So here you see what Rolf Storms and Claudio Carrera studied in flocks of starlings. And the flocks of starlings react to the main predator, the peregrine falcon, by usually blackening, like you see here. Sometimes an agitation wave. An agitation wave is that you see dark bands in the flock moving away from the predator. And then sometimes it leads to splitting, like with this pseudopodia, it could lead to a split. And these splits are, these subflocks merge again. And often you see also a flash expansion here. The predator attacks indeed at the periphery, and then the birds flee in all directions, and so on. Here you see how the peregrine falcon attacks at the periphery, rather at the periphery, and you see that the birds, so it flies inside the flock a bit, and then you see that the birds flee away in all directions. And this is rather easily studied. What we showed is empirically, by checking, by analyzing data from attacks, that if the predator comes from above more, in that case it dives more. Of course, it goes faster automatically. Then you get more often a pattern of flash expansion. But you have also another pattern of collecting escape, and that's this agitation wave. And then you see that dark bands move away from the predator, from the peregrine falcon. And this is very difficult to say what happens here, because these flocks are far away, a kilometer away. So we don't know what underlies this collective behavior, and this we studied with the model. But empirical data showed that it seems to reduce the predator success.
So can I ask a question?
Yeah.
Because also in the physics world, we sort of, or some physicists claim that these agitation waves can be described by what's called the Toner 2 model. Is that something? Because this is like a density wave. It's like some areas of
you keep your question. I'm coming to this. Yeah, okay. You keep your question. Because indeed, this could be a density wave, yeah. But is it? Because it could be something else. And that so we think there are density waves in schools of herring. There you see these dark waves going away from the predator. But in schools of anchovies, what we see is that the fish, and they have a silvery belly, turn around. So they make a kind of skitter motion, and then you see suddenly the silvery belly. Or in dunlins, what we see, they have a white belly and a black back. We see that suddenly the flock may turn a different color. So then we get these waves as a kind of wave of orientation of the bird. Like you see here, this is filmed by a student. These are dunlins, and you see they avoid a predator, predator or gull, I don't know. And then you see the back and the front of the bird. And if you would see, if this would be happening in starlings, if there would be a wave of orientation, suppose that the birds make this zigzag maneuver as skitter motion, the starlings, then they would roll, because of the turning, roll over their shoulder. And if they roll over their shoulder during the turning, that would mean that we from the ground see a different surface of the wing. So kind of, if you see me flying like this, you see more wing if you are below me or above me than if you see me flying like this when I'm turning. So you could imagine that the dark waves are due to a skitter motion indeed by the starlings, a skitter motion, copied by others, so a group of starlings doing skitter motion, so we see more or less of the wing area, which would be the dark band. So we studied this in our computational model, so we have this normal computational model, we say here is the predator attacking, then we give the birds nearby an escape maneuver, and then we make other birds repeating this escape maneuver. And no more than, they mind only maximally 7 neighbors. And then we look at these 2 escape maneuvers. One escape maneuver, like you suggested, that leads to a density wave. So the birds flee away from the predator, come too close to others that flee away from them, and so you get a density wave moving away over the flock. Or we make also a zigzag maneuver whereby the birds make this zig turn, and the zig turn is accompanied by, so the zig maneuver, this turn is accompanied by rolling, by banking, and banking means that we temporarily see more wingspan or less wingspan, and the black part would be then seeing more wingspan. So the black bands can be due to us seeing more wingspan due to an orientation wave, or it could be due to a density wave. We studied this in the model. And here we make the predator attack here, and now the wave is going through the flock, in the sense that here first a few individuals start fleeing away, speeding up away from the predator, and then the others copy it, and so you get a speed up wave, you get a density wave that's moving through the flock, but we don't see it. We don't see this density wave. It is going through the flock, but apparently that's not what is going on in the agitation wave in the flocks of birds. So the agitation wave is not a density wave. So is it perhaps an orientation wave? And then here we make the birds move away by orientation. Yeah. And here you see that indeed, if the birds make this skitter motion, you see the dark bands moving away from the predator. So here we show it again for the model. You have here a model predator also, and you see that if the birds make this skitter motion, rolling temporarily, the zig maneuver, then you see a kind of an agitation wave. Now you can still argue, you can say, okay, the agitation wave in starlings is probably an orientation wave. But it could still be that also in our model, that when they make the skitter motion and roll over their shoulder, they come a bit closer together. And to study whether they come closer together during the skitter motion, we need to get rid of the shape of the bird. So we made the bird into a ball shape, and then we give them the skitter motion. And then if we see dark bands there, it would be just due to also a density wave at the same.
Just a question, dark
Yeah.
band, what does it mean when you show it dark? It's like you change the colors, like the ones which are going. Like, I don't know how you define dark band here. Is it like change of? Is it a change of density?
No, it's not change of density, but it's change of what you see of the wing space, wing surface. Look here, if I if I fly like, if you are below me and you fly like this, it's a lot of wing space. But if I fly like, if you fly like this, you see very little of the wing space. So these birds are making this zig maneuver, and to make the zig maneuver, they have to roll over the shoulder, so you can see. If you are below me, you see much less of my wing. And if you are below me, you see a lot of my wing. So due to the change of orientation, you see more or less wingspan. And that is what causes the dark bands in this model here. But at the same time, you could have a density effect. So this you can study by making the birds in the shape of a ball. If you make the birds in the shape of a ball and you give them still this zig maneuver through when they are attacked, then you see what is the density effect of, in the model, zigging. And so here we start the birds at the same position, and you see that, oh, dat gaat mis, that there is no wave here. There is no wave here, maar dan snap ik niet waarom dit even aan. There is a wave here, but there's no wave here. Nou, zal ik het even begrijpen? This is what I wanted to have. Here you see the wave, the zig are going through the flock of ball-shaped birds that are at the same position as in the other one. And you see that there is no wave. Whereas for the same starting position, if you see them in the bird shape, you see the wave. And here you don't see the wave. Yeah? So the motion of the dark bands is merely due to banking, not due to density in the model. And then you can ask something else. You can say, okay, there is a certain speed of the dark bands moving over the flock. So the agitation wave in itself has a speed. And this is often very fast, perhaps, and then maybe there is long-range anticipation needed for these dark bands to move in the flock, like in the, yeah. But what we see is that the average speed is only 13.5 meters per second, which is not very high. And if we look at the different events, we have 15 empirical events indicated in blue. You see that the speed of the wave ranges from 3 meters per second to 25 meters per second. And you see that in red, we can easily make the same speed of the wave. So we make the speed of the wave faster by giving more individuals the opportunity to copy the escape maneuver. So if you have only one individual transferred to one other, it's slower. But if one individual transfers the escape maneuver to 7 others, it's much faster. Also, if the density is less, so the individuals are further apart, then if they transfer it, the wave is faster. So we can easily, by making birds repeat the escape maneuver from 2 to 7 neighbors, and by changing the nearest neighbor distance from 0.7 to almost 2, you get these speeds.
So this question, the wave speed will not depend on the observer as well, because if
No, because you measure the wave speed relative to the flock.
Oh, okay.
Yeah. And so the wave of agitation in starling flocks is not a density wave, we think, and we think it's an orientation wave, a banking wave. Answer to your question, I think, because of the large changes in due to the large changes of visible surface of the wing. And the speed of the wave is due to local transmission to 1 to 7 of the closest neighbors. And these are hypotheses for empirical data. And we looked at the agitation waves in the empirical data again. And we wanted to know in the empirical data whether perhaps these agitation waves, these dark bands, fade out over time. Now, if you have a normal flock that is turning, we've just shown that there is nothing that fades out. All the birds turn at the same speed, the same curvature, nothing fades out. But you could imagine that if you have the very different case of these pulses go through the flock, of these skitter motions, pulses go through the flock of fear, maybe that fades out over time. So we study it first empirically with Andrea Costanzo, a physicist, and then we study it in a modeling study. And here you have again this empirical case. You see that the peregrine falcon attacks, and you see here dark, white, dark, and then the wave goes down. So at the beginning of the starting of the wave, you have difference in elimination, dark, less dark, dark. There are pulses going. And at the end of the wave here, you have also dark, light, dark. And so he has interpolated these frames over a second at the beginning and at the end of the wave event. And he measures the illumination, in these wave events. And so what he sees, for instance, for one wave event is that the amplitude at the beginning of the darkness, the luminance or the darkness, is like this. I can make it again like this, wait a minute. It's like this. And at the end of when the wave has gone through the flock, it's like this. So you see that the amplitude has gone down, so the wave has faded out a bit in this case. But you can also measure per pulse. So you have the first pulse, the second pulse, the third pulse, the fourth pulse, and then you see, I'm going over time. If you want me to stop, it's fine. But it's also due to the questions, so it lasts till 2:30. Yeah, okay. Okay, so then we have to go over time because it's due to the questions. Okay, so then we see here the same for a wave that you can have several pulses. You measure the amplitude in illumination, difference in illumination, and you see that in each case also here, the illumination, change in illumination at the beginning location, the start location is larger for the first pulse than at the end, for the second pulse, then at the end, for the third pulse, and at the end, for the fourth pulse, and at the end. So he studied per wave the change in amplitude, the maximum amplitude, difference in amplitude at the beginning and at the end. And this is significantly decreased. And you can measure this also per pulse at the beginning and the end. And you see that combined for these 5 flocks indicated with different colors, this is significantly decreased. So in the empirical data, the wave fades out. Fine, that's new. That's different from a turn, which doesn't fade out, a collective turn. And now, is this fading out due to the individuals having less wish or less motivation to do the scatter motion? Or is this fading out due to everybody still doing the scatter motion, but doing it less eager? So making a shorter angle, less of an angle. So at the beginning they make a big angle, and at the end they just make a small angle. We studied both, is it clear? They turned over a small rolling angle, banking angle. And we studied this in the model. What's the cause of the lower amplitude at the end of the wave? And in the model, if you have this difference in amplitude, you see that the difference in amplitude is larger in both cases if you have a lower probability of copying, but also if you have reduced banking. And only in case of reduced banking, it's significant. So we think now that over time, the agitation waves and flocks are starting to die out, that's one thing. And how do they die out? Our computational models suggest that this happens rather by the birds rolling in the end less deep, so they're maybe less fearful, less intense, than having less tendency to copy the zigzag maneuver. And this seems adaptive because birds that are further away from the raptor obviously experience less threat, so they're less eager to make this zigzag, or they make a more sloppy zigzag. And then the last part before the questions is that you have also this darkening in the flock. And one of the collective escape patterns is darkening, like you see here. And how does this come about? Is this indeed something like going closer together, density increase? Or could it also be because we see the wing surface differently? So it's an orientation effect. And Andrea Costanzo studied this in the model by putting in the center or even at different locations an observer in the model, and then having the observer observe the illumination changes. And then he saw, which you can see here, that the illumination is lowest when the flocks take turns. And the illumination, which we don't show here, is not changed by changing density of the flock, by orientation of the flock under different angles towards the eye of the observer. This strong difference in darkness came only by this orientation effective orientation. So questions about this part? Yeah.
Yeah, can I go back to my question because it was not exactly answered? So my question was about the collective, so these density waves or polarity, or what do you call it, orientation waves?
We think so, yeah.
Yeah, they both feature in this thing that we call the Toner 2 model.
Okay.
Because there's a velocity, there's what we call a pneumatic vector, which is the polarization vector or alignment vector, and there's a density.
Yeah.
And you can use that model and see that there's, these two types of waves. I was just wondering if people had actually tried to compare that with this.
But this, no. But I think it would be interesting to compare. Yeah, they didn't. Yeah.
Okay. Okay.
Yeah.
A comment along this because these are like continuous models, and typically when you get a polarization field for the orientation, you get a density field for the density locally. Typically, they are coupled. So in this type of models, because if you create a density wave, it can lead to an orientational wave, and the other way around. So, but from what your data, apparently you can create an orientational wave, but no density wave, as if they are decoupled.
Absolutely, they're totally decoupled. Yes, totally.
Yeah, so
Yeah,
it's
they are.
a specific regime because as I remember from this Toner 2, they are typically coupled, the equations, they are not decoupled. Like
Yeah, but here it's a different thing. And you have to, if you think in terms of birds with wings, then of course they could be closer together, the birds, or they could be under a different angle how you observe them. Yeah.
But not both. I mean, that's the question.
yeah. That's
You can also be both. Yeah, I can't acoustically. I have difficulty acoustically to understand it. It could be coupled, but I show that it's not coupled in this case because if we decouple it by having the skitter wave, in this case they are not closer together during the skitter wave. Is that what you asked?
Yeah, thanks. Yeah, I am just surprised. Yeah.
Yeah.
Because in the other models, typically they are.
Yeah.
No,
Yeah.
but the other models, you can also find a regime in which you freeze the polarization and have only density fluctuation.
What about the other way around? Because what they see is the other way around. They see that there is you freeze the density and you have.
Yeah, I think you can do
polarization
the same. You can freeze the density and have just a polarization wave.
wave.
I think
That's the regime they see.
yeah, no, it could be, but I think the Toner 2 has both regimes
Alright.
and has the coupled also, in which you fluctuate everything at the same time.
You showed that it actually was, if you took away the rolling, that you get this wave, right?
The rolling, yeah. If you do, then you get this wave. Not if you take away the rolling. The rolling is causing this wave. So like.
You get these waves. You don't get the waves if you take away the rolling.
Yeah, you don't get waves. If you
Yeah,
take
so-
away the rolling.
yeah,
But
so-
I didn't show that I took away the rolling because if I make the birds into a ball shape, they still roll, but you don't see it.
Yes, yeah, so it's the reflection, yes. True.
Yeah, so it's the area of the wing. So you see a lot or you see less. So you see less wing area, you see a lot of wing area. Yeah, okay.
Yeah, so my question is then somehow, can you also take away the density effect? Because
We have no density effect in it.
I have the feeling that you take away one of the two effects, the density and the skitter. You take away the skitter, but not the density effect, but not you don't do the reverse. So whether
Wait a minute, we took away the density effect of, let's say, the if we show the density effect, you see nothing. We want to know, the question is, what causes these dark bands?
sure.
If we make a density effect, a strong density effect, a dense band go through the flock, we don't see it. And then let me show it again, because that's
Yeah, you have these two movies next to each other that you compare, and in the this one, yeah. so
no, this is the ball shape, yeah.
That's the ball shape.
Yeah. Okay, now I have to first go to the other one. I think the moet je eerst. I have to go away from this one, okay? Because that it only works if I go away out of this thing. Oh yeah, so yeah, good. Yeah, I didn't know that. Okay, this is the skitter motion, and this is the density. Here, a density wave goes through the flock and you don't see any dark bands. The question is, what are the dark bands? They are not a density wave. The answer is, the question is then, are they a skitter wave due to a skitter wave, which means that we see larger surface temporarily of the wing? Yes, they are due to a skitter wave. What we don't know is whether during the skitter wave, due to random motion, and so we also have a density wave. So, but if we make them into a ball and we have the same skitter wave, like you have here, here you have the same skitter wave going through the flock and you don't see anything. So there's no density wave or anything leading to, yeah.
But don't, I mean, maybe I'm more bigger fantasy than other people, but it feels like there is something moving through this thing.
Yeah, but that's not the question. You have to go back to the question. Our question is, how do you get these dark bands that we see in nature? How do we get these dark bands? You don't get them if there is a density wave, because we show a density which you don't see in the model. So it's not due to the density wave.
So levels.
Unlikely, what?
So if you assume what you do, that this because of the banking, you also said earlier that when you bank, that these birds also have to go down because their lift changes.
Yeah.
So that would mean that in these videos, you should be able to find a correlation between dark bands and moving down.
Yeah. Now the thing is that we didn't study it in that detail. What often happens in nature is that there is a vertical flock, and we don't know exactly what happens there. And there you also see dark bands moving down, like I show here. And we didn't study that.
I'm not talking about
so we can't.
I'm not talking about the waves moving down. I'm talking about the individual birds moving down.
Yeah, but that's only a little bit. So that's only a little bit. So that is not, these flocks are not so large.
It's not something you could measure.
Yeah, we could measure it here, but why would we? This is not our question here.
Because that would some sort of empirically prove your statement that if the dark bands are due to banking, and you can actually prove that when in these dark bands, the average movement of the birds is downwards.
In that case, you prove nothing, because basically in reality, you would prove it by having very big cameras, which we don't have yet, and then see in nature whether you see that they indeed are, which I think it's true, the orientation wave. But what I mentioned is, in reality, often you see it like this, the agitation wave. That makes it even more complex. And we don't know exactly how this happens. So you have agitation wave to the side, we only studied that. I don't see what it would help if we here had also, which is true, you're right, they move a little bit downwards. And I don't think it would help here.
And maybe, I don't know about the time scales to go down, because when you have the full flock started without agitation, you would expect that it takes a bit longer to go down, and the agitation seems to be
probably time scales not long enough to actually.
Yeah, good point. Yeah, I don't know, I didn't realize the answer, yeah.
Do you also see these agitation waves in fish in schools?
Yeah, in fish,
because it's a good orientation.
Yeah, you see it a bit in the sense with this fish which has the silvery belly turning upwards. There you see this wave. But you also have density waves in herrings. Now,
but as you showed before, fish have more variability in their speed, and so I would expect density waves to play a stronger effect.
Yeah, that might very well be. What we know so far is that in showfish they have this wave where they turn up their belly, but there is a density wave. It's argued in herring. So it might be this. This is indeed a question for further study. Yeah. And then shall I go to the last part or not? Yeah. Shall I go to the last part now? Which is shorter. Okay, so then the thing is that it's very difficult to study empirically such things like agitation rates and so on. And also to study for other birds patterns of collective escape. So we developed a robotic falcon, like you see here, and such a robotic falcon is of course very useful also, a peregrine falcon, also for cleaning up air bases, where you have a lot of collision between airplanes and birds, and it's really dangerous. Particularly it gets more dangerous because you have more airplanes and more collisions, because they are also more silent and they are faster, these airplanes. This is a robotic falcon, and we first study what it does. And so here's a flock of pigeons, and these pigeons is a cooperation with University of London. These pigeons have on their back a GPS, which means that we have the trajectories of these pigeons. And what you see here, and now I can make this thing red again, laser pointer, now, is that this is the robot falcon, this is the robot falcon, sorry, and this is collective turning of a flock of pigeons. And on the back of the robot falcon, we have a camera. Oh, I didn't show that maybe so clear. Here you see on the back of the robot falcon a camera, which means that you can see, so the controller steers the robot falcon looking from the perspective of the robot falcon. And this is what you see here, how collective turning happens of flocks of crows. So you have two views, from the ground and from the perspective of the robot falcon. And we studied this with models and empirically, and interaction between the two. And now, does this work at all? And here you see that over time, on the x-axis, the percentage of sites cleaned from birds within 3 minutes is 100% if you chase a flock with a robot falcon. So suppose there's a flock of birds on a meadow, and you come there and you fly towards this flock, then it flies away within 3 seconds. Within 3 minutes. 100% of the flocks. If you do this with the drone, this one, 75%. If you don't do anything, about 5%. And now the big issue in this area is that at the air bases, of course, they're trying to get rid of these flocks of birds. And they are doing pistols in the air, which, how do you call it? And they do lots of things, but the birds always get habituated. So the thing is, do they get habituated to this artificial falcon, robot falcon? And they don't. And that is what you see here. Here we measure on the upside axis the distance at which flocks flee away from the robot falcon when it approaches. And you see that this distance, flight initiation distance, stays the same over time. On the x-axis, you see the time from the beginning of August to the end of October. And you see there's no difference in the distance at which they fly away from the robot falcon, neither for lapwings, corvids, gulls, or starlings.
How did you know that they are the same flocks?
You don't know that they are the same flocks.
Okay, but then how do you say, why do you talk about habituation? Because habituation only occurs if you are repeatedly exposed to the same stimulus.
Yeah, so you could say like this, we have no indication at all for habituation. And the same flocks, it's a good point, the same flocks usually will be the corvids, because the corvids have a territory and they stay at a certain location, and then probably you have the same flocks. But the reason is a bit more than this one, although I totally agree, because they can't distinguish the robot falcon from a real falcon. I'm convinced, because I can't. So why does this work at all? So what we do, we chase away with the robot falcon these flocks, and they flee out of sight of all these species within 3 minutes. They stay away for hours, and they do not get habituated. We have no sign at all that they get habituated. Well, why not? Why does this work and the other methods usually don't work? And we think because it resembles very much a real peregrine falcon. Here you have a real peregrine falcon attacking this flock, and it's you see that the flock shape changes and so on. This is the peregrine falcon. And here you have the robot falcon attacking this flock, and you see that the flock changes a bit shape and density. It looks very similar. And this means that we think it's a suitable method, this robot falcon, to attack flocks of all kinds of birds and study their patterns of collective escape. And well, we discussed already a number of patterns of collective escape. You have that if you attack a flock, that it collectively turns away, or you have that it compacts, maybe it becomes darker because it compacts, and it looks like compacting. You see splitting of subflux, you see merging of subflux, blackening, flash expansion, agitation wave. Okay, we studied these patterns with the robot falcon in the real flocks for these 4 species. So you see the corvid, the gull, the lapwing, and the starling. And what you basically see is the starling shows all these patterns of collective escape, but the corvid, gull, and lapwings mainly show patterns of collective turning, probably compacting, splitting, and collective diving. And what we see is that they show these patterns relatively in the same order. I mean, all these 4 species show most often collectively turning away from the predator, secondly, most often compacting, and thirdly, most often splitting. And well, we don't know why they prefer, or we don't know why they prefer to collectively turn away. We don't know. But it would be something interesting for modeling also.
And still, the movies that we see always show these kind of darkening patterns of agitation waves. And from your previous graph, those are very seldom.
Yeah. Yeah, so we have studied you talk about starlings, absolutely. So we've studied the seldom this, yeah, indeed. But this is when we wait a minute. This is when we attack with the robot falcon. Right. When we attack with the robot falcon, we very seldom have here from Friesland these very big flocks of starlings, because the pattern does happen. Agitation wave does happen relatively often in starlings. I think 26%. And then we go back to it's almost done. Here you see agitation wave is 26. If you look at above Rome, at flocks of starlings which have large size, 26% is this and blackening is that. Yeah. But if you study them with the robotic falcon, then you usually don't have 2 big flocks. And that is the cause, I think, that you have here not so often this agitation wave. Yeah. Okay. But you have a point. Yeah. Anyhow, what we see then is this order. And then, of course, this needs for modeling, if there's a need for modeling. And we have done modeling, Marina Papadopoulou, for the case of the pigeons, because the pigeon flock, on the birds, on the back of the birds, there is the GPS. So she measured the trajectories. They measured the trajectories of these birds in the flock. And what she observed in the data is that there are 2 patterns of collective escape only in pigeons. They only show this collective turning, and they show splitting. And then what she saw is that the individuals that initiate the turn, if they turn with a greater angular velocity, like you see here, and in the empirical data, is more likely to lead to splitting. And if they turn with a smaller angular velocity, it's more likely to lead to a collective turn. And she shows the same in her model. So this means that there's only one parameter causing this means that by one parameter only, a single trait only, the angular velocity, the whole flock will show 2 types of collective escape, either collective turning or splitting. Yeah, it's almost done.
You also model directly the falcon, or someone models the falcon? Like,
we don't model the falcon here. We have another PhD student modeling the falcon, but not together with the flocks. Yeah.
But I mean, because the hunting, if you want to be similar, the like robot falcon should hunt has a falcon. So more when you perform the experiment, how is this hunting?
Is there someone controlling the robot?
Yeah.
Yes, oh, sorry.
Yeah.
The robot, yeah, but okay. Yes,
There is somebody controlling the.
wait a minute. So here you have the robotic falcon attacking a flock of starlings, and this is controlled, of course. I was not clear. Wait a minute, I show you again. Here you see the person who developed the robotic falcon, Robert Musters, and he controls from a distance the robot falcon, which I think, yeah, and looks through this camera. So together with Rolf Starms, who looks from the ground, who says you have to go a bit to the left. If he loses the flock, go a bit to the left, go a bit there, go a bit there. You have to do it with two persons. You have to have the view from the ground and the view from through the bird. Yeah. So this is controlled like that. Yeah.
But his question was, does this person have to mimic the pattern that
Yeah.
the fact? Okay.
Yeah. So if the question is, the robot falcon is steered as much as possible like the real falcon attacks. That's what you mean?
Yeah.
Because the person, Robert Musters, is a falconer, so he knows pretty much. It's not exactly the same because the maneuverability is still less of the robot falcon. But the thing is that you wouldn't see the difference. And I have great difficulty to see the difference. I'm a bird watcher rather, but for it's difficult. If you see a flock reacting to a robot falcon, you don't realize, okay, that's a robot falcon. You would with a drone because a drone is less maneuverable. Yeah. Was that the question? Yeah. Okay.
But
So
I-
then, yeah.
But I can imagine that this robot falcon, it's a fixed structure, so it cannot just pull in its wings, or can it pull in its wings? Does it have the flexibility?
Robert Musters made two robot falcons. One that is flying by the wing, through the wing beat, and one that's not flying through the wing beat because it's better maneuverable. And he didn't find a difference. And so we continued with one in the reaction of the flocks. And so we continued with the one based on the relatively fixed wing. It flaps a bit. Yeah. But that is different. So this is in the model, and then Marina Papadopoulou, studied first the pigeons, and then she studied what is happening also in flocks of birds and in flocks of starlings, because they're so large. You can see two patterns of collective escape at the same time in one single flock, and that hasn't been modeled, and neither by her. But here you see it. For instance, the robot falcon is attacking, and you see that here a cordon emerges. And then a few birds dive downwards, and then you get a split. So here a few birds dive downwards, they do collective turning, there gets a cordons, and then, and so she thinks that what happens here is that the robot falcon attacks, you get this collective turn, some birds dive downwards, and then diving downwards, and then you get this cordon, and then you get a split. So you have sometimes several collective patterns going on at the same time in a flock. And that will be something to study also in models. And what I've hoped to have shown you is that self-organization models can help us if we put cognitively simple behavior rules in the sense of that they mind only a few neighbors in the model and make the individuals interact, and then study how by self-organization complex patterns emerge at the group level. And this gives us some understanding by building the system. And as we like to thank all these people and these grants. So more time for questions.
So I have one question. So I have heard the rumor that when biologists want to model flocking, they have models with something like 30 parameters. Is this a true rumor, or which is very different than yours, right? You have some parameters,
but still we have a lot of parameters. But I want to say that's not so bad, because you want to study something in nature that has a lot of parameters, many more, of course.
Yeah. But how many parameters does your model?
I don't know exactly, but I think if we look at the beginning, that it's about.
You showed a table with maybe 15 or so.
Yeah.
Is that?
But that's not in the flock, but that's also. But I mean, that is life, huh? We study life. You can say, let me give you of course you want to study a model, but let me give you an example. You can study lots of things without including space, and then you say, okay, it has less parameters, but lots of things have such an influence of space that, of course, it's irrelevant, the model almost, or the model is worse if it's not including this.
So it's about 15 you have or something like that?
Yeah, I don't think me. I can't look it up. I think yes, but this also but lots of them are empirically. They're not free parameters. Huh?
Yeah.
It's not free parameters.
Okay.
Maybe you're interested in free parameters. It is the weight of the bird. It is the thrust and the etc. The gravity etc. And then it is the reaction time etc. And these things we got them from empirical studies. So then these are fixed. These are not free.
But you can verify them in independent experiments.
Yeah, I find this, if you can measure them, each of them, sure,
So,
I understand.
one of them was the 36 km/h speed, for example, in the table.
Yeah, sure, so.
And the mass of your bird, and that kind of parameters are,
Then each individual in the model are equivalent, or there's variability in the mass?
No, we make them same weight, but but the remarkable thing is they are not totally synchronized.
Yeah.
So you see it as if the dark bands move over the flock are totally synchronized, but that's just because our eye is not fast enough. Our visual system is not fast enough because they have their own moment that they react. So you have the time to say you have time. The birds react are updated with a certain very short interval, but they also have a reaction time, and they are not synchronized with the reaction time. So I do think that also this explains a bit that we are so astonished about bird flocks changing Dunlop flocks their color. That's how fast they can react to each other. Yeah.
Has anyone taken these models and coarse grained them to find a continuum description of them?
No.
I was wondering, so lots of questions you ask would be answered if you would be able to track these kind of swarming birds by individual birds. So how far is the camera technology coming along into actually studying these flocks and tracking individual birds and do correlations or?
Yeah. So the camera at the time, at least, I don't know now, right? It was not good enough. We have seen a number of photographs where we thought indeed this probably an orientation wave, the agitation wave. And at the same time, you would also GPS, because if you have GPS on the back of the birds, you can, well, that's too heavy and too many. There are too many birds, the starlings, too many. And the wild starlings, I mean, you would have to collect them. I don't know, there are 20,000. I mean, yeah.
But GPS, is it accurate enough? Location.
That's
distance?
another point. Well, we had GPS on the in cooperation with London on the pigeons. Yeah, I'm not sure how accurate. I see your point because the starlings are smaller and they're more maneuverable, and then it makes Now they are 1 meter apart still, huh?
But it has to be very accurate because when they do swarming experiments with drones, I mean, they can make them really close to each other without crashing, and that's a GPS sensor also. Right, the gyro, whatever.
No, but I think the swarming experiments are often with pre-designed routes, isn't it?
I don't think so. Yeah,
I think so. Yeah. Okay. I think so, and that makes a big difference. You see, if you have a pre-designed route, you don't look at the same speed, of course, you're going to collapse. Yeah.
I'm a bit confused by that the splitting of the group happens so often because if you say that like there's 16 numbers, it doesn't really make sense to me that they split.
Yeah, and indeed, the point is also that often a few birds are. So if the predator attacks at the periphery, often he splits off a few birds, and we think, biologists think, I'm not sure, that generally those are the weaker birds, that they're a bit slower and so on, and then they're eating indeed.
Yeah.
Yeah.
Because I know from fish schools that it's actually one predator, it's very hard for one predator to split up a group, then if they work together and it works.
Yeah.
But you see it here with just one predator.
Yeah, you seldom have several predators attacking a flock, seldom, and seldom cooperating. There is the story of they're in pairs, peregrine falcons, that sometimes the heavier female attacks from above and below there is the male and attacking them also, but that's only within a pair. There's very seldom cooperation. It's not, we've been thinking of modeling that and also been thinking of driving away flocks with two peregrine falcons, roboted falcons, and we've tried it once, but I mean, in nature that happens seldom. Yeah.
So I do remember from watching nature documentaries that there's like strategies by dolphins to drive actual fish into groups, like as a hunting strategy.
Yeah.
But you mentioned that it's actually advantageous for the prey to be in groups. Whereas for shoals of fish, it might be a good hunting strategy.
Yeah, this happens seldom. This happens. I totally agree with you, but this happens very, very seldom.
Yeah.
So the most frequent what you see in nature is that flocks are attacked.
In birds, you mean?
Oh, but also in fish.
Aquatic systems, you do see it in dolphins, right?
Yeah, but dolphins is just one case. I mean, most fish are in schools and show that many fish are in schools and they are attacked by single predators. A few predators.
So it's advantageous for the prey if there's only single predator attacks, because it's harder for the predator to target specific prey. But if the predators are in groups.
Yeah, this happens seldom.
Yeah,
this happens less often. Yeah.
It's also, it depends on the size of predator, and especially the type of. So many fish predators are gate limited, so they have to target one single individual to actually be able to catch it and eat it.
Yeah, that's why I was wondering why the falcon doesn't go with open mouth and
exactly. Yeah,
just grab one.
It's rather pretty long. It takes at least 20 minutes in the evening when these huge flocks are there. With thousands of individuals, it takes at least 20 minutes before he or she catches them. Yeah. It's a really long time. Yeah.
Maybe comparing the fish with the birds, is it a single model of different parameters or
no, different models.
Different models.
Yeah,
So you cannot really map.
No, different models. Yeah.
Cool. Let's thank the speaker again. Down there.